Thank you. Recording is in progress. So we're repeating input and output impedance here. Zn of a two element voltage divider is just the series sum of the two elements, their impedances. And for output, it's the Thevenin impedance, Thevenin equivalent, which in this case is simply Z1 added in parallel with Z2. Yeah, so to be careful, it's the Thevenin resistance of a two-element voltage divider, right? I mean, if you had more resistors, we've seen in general, it's somewhat more complicated than that for the Thevenin decomposition. But we like to make our lives easier, so we're going to almost always be able to think in terms of a two-element voltage divider. And let's see what's next. Phase shift right. So we haven't gone into it yet, but we have noticed a phase shift. We do know something about Bode plots. Notice this Bode plot is what they did is they took the frequency and they divided it by the 3 dB point. Oops. It's not critical, just so you know what you're looking at. And then that way you could compare any circuit. And the 3 dB point, see there's one of them, is the square root of 2 over 2. But what I want to discuss is the basis for the phase shift. Hopefully we kind of understand why the output changes, because the capacitor and then in the oscilloscope lab and the inductor are both frequency-dependent resistors, variable resistors. So instead of turning a knob on like a potentiometer, we change the frequency and we change the resistance of a capacitor or an inductor, or in a general word, we change its impedance. Generally, when engineers and scientists use the word impedance, they're talking about input and output, or the impedance of a wire, cables. And we haven't gotten that discussion yet, but these coax cables come in different forms. They've 50 ohm form, there's 75 ohm form, that's the one that TV cable uses because of the frequency that goes across for TV signal, cable TV. 50 ohm is the best general purpose, but we need to learn a lot more, and it's something that I understand deeply that I couldn't explain it right off the top of my head, but we'll get there. So in the oscilloscope lab at the end, we did something like this. There's an RL involved. We didn't get into that, but I guess I should at some point talk about the effect of that. But the first thing we want to notice, and we haven't looked at inductors just yet, and notice that the legend, this is I, this is V, and this one is I, and this one is V. So notice that they do opposite things. So I'm hitting it with a square pulse, on-off switch, and in this case it's the charge cycle. And the only takeaway from this is that you notice that the capacitor, when you charge it, instantaneously has a high current and a zero voltage, and the inductor is the opposite. That's all we care about right now. They're the opposite, but also that the I and V don't match the input. At first, the I's match, but the V won't. When I hit it with a V in, the V out in the beginning is different, and in fact, eventually it becomes the V out. So you see that with a capacitor, the V out lags V in. Sir?
What are the axes here on these?
Sure. Time and either I sub 0 or V sub 0. I should have done it in time constants. In fact, if you're clever and it's arbitrary, I don't know what it is, it's just arbitrary units, I should have done it in time constants. And you may notice that it's less than 5 time constants because they're not plateauing. I wanted to focus on the changing area. You might argue that this one over here made it to almost 5 time constants. But all I want to take away from this plot is that they operate differently. That's it. Back up. I can't hear you. Open your mask for a second. Side 2? Okay, I'm sorry. This was, we already went over. That's why I went over it quickly. Sorry. Yeah, notice that it's the, this is R1 or Z1 plus, excuse, come on, Harry. You can better be, but you have to be better than that. Draw menu, erase. Yeah, you might have to stare at that one for a moment or two. And you should notice that this is Z1, Z2 divided by Z1 plus Z2, which is the parallel, a 2-element parallel equation. They look exactly the same, but the top one has parentheses. Oh, right below it in red, I did it already. Okay. You're welcome. Maybe somebody else wants me to stay there? Okay, well, we'll find out. So this part is what we're building on right now. This part, the Bodhi plot, we've already seen. And remember, it's minus 20 log 10 V out over V in. The minus sign is that it works out then that a passive filter, it can't amplify. So whatever it does, it produces negative, and amplifiers produce positive. Of course, one could argue I could just flip V in and V out, but that's not intuitive. It means I have to memorize more things. So the figure of merit is always V out over V in. It's a question of how we present it. Remember, we used V out over V in when we were calculating the impedances as well, as a function of frequency. And we're going to work on adding that to our spreadsheets in a little while. So this is the circuit you do in the oscilloscope lab. Well, one of them. You measure the 3 elements, and in the case RL is built into the inductor. So we have an R experimental we used as well, but you don't, when you do this measurement, you don't use the R experimental. The R in the inductor is good enough. What I wanted you, though, to notice that in these plots, so one of them is simply you have your R standard and you have your R cap, and the other one is your R, to just tie it in with the oscilloscope lab, and the inductor. Or Z, and I keep mixing up R of L. I'll just keep the Z. And that's if I put them, remember this is the device under test, right? So we generally are just looking at the voltage. And we see that the voltage out lags behind. And we say the voltage out for the inductor is ahead. It's not obvious from this picture, though. But the most important thing is that they're in opposite directions. And that's why when you notice that when we do, when we have a ZL plus ZC, it's 2 pi of FL minus 1 over 2 pi FC, because they react in the opposite directions. All I want you to take away from now is that something happens to the voltage and the current in both of these devices. They're reactive devices. Okay. So remember, now this is called a phase diagram. It's a phasor diagram. And the phasor is the applied current is along the phasor, the maximum. And what we measure in the outside world is across either the resistor or the inductor or the capacitor. And so you imagine the phasor rotating to the left has to do this. Oh, what is this? The Euler. This is called the Euler relation. I hope maybe you've seen this in mathematical physics. It's very useful. And this is also one of the first times that you get to understand why we use imaginary numbers, because we can encode information into the imaginary number, but when we take a measurement, all we care about is the real part, the projection onto the real axis. I don't know if any professor has ever said that to you before. I know mine never did. It took a long time for me to figure it out. So you notice that when the phasor crosses the y-axis, the output is at 0 because that's the imaginary axis. Now, this is mostly to give you a sense of what's going on. I'm going to give you a more intuitive feeling for it. I took this out of the Physics 2200 textbook, and I've been refining it because I don't think they do a very good job, and I don't think I'm doing the best job in the world. But it's just too good of an opportunity for you as physics majors to give you a sense of why we use the imaginary numbers in physics. They were kind of invented as a curiosity, the square root of -1, but people like Euler, all these French mathematicians in the 1700s, they realized, well, I guess Euler is German, but French and German dudes figured out that we can use them to carry information. If you've done modern physics, you know that you've got a wave function. There's a real and imaginary part, and then you take the complex conjugate to find out the value of the probability function, right? And a lot of times your answer is simply the phase shift, and that comes from the imaginary part. Okay, so let's back up a step and look at it in little pieces. If we have ourselves a simple resistor, if we measure the voltage across it, we know that that voltage is I times R, and it's always a simple relationship like that. And there's nothing that depends on frequency. So if we were to measure I and V separately, we would see that they line up with each other. and we go to their, what they use, and the I and the V vectors are always in line with each other, and the V out is always the projection of the resistance onto the, and the multiplication VIR onto the real axis. But of course, if we put a sine wave into a resistor, we get a sine out. Yeah, I should set up my circuit here so we can actually look at these things. I'll set up this. Okay, let that boot up. What's next? So now we have both of them, but we've seen these before. The reactance of an inductor is 2 pi FL, and the reaction of a capacitor is negative 1 over 2 pi FC. Whoops. That writing, okay, people are still writing. Alright, now let's go to the next slide. So if we look at the voltage across the capacitor and the current in the capacitor, what we see is that the voltage is ahead of the capacitor. I always get this wrong. So this is the now, and I keep going. Oh, I can never get it right. I thought I wrote it down here. So, well, let's just look at what happens is they develop it as the current lagging, but we don't directly measure the current. We measure the voltage across the capacitor. So I want to make sure that what I show you is consistent with what you see on your oscilloscope screens. And let's see now, we want picoscope. So let's study it for ourselves. If I can find, it's right in front of me, there it is. And there it is. Oops, well, let's hope. We'll turn this on manual. Okay, so now, or actually I said manual, let's make these comparable. So the blue is the V in, and the red is the V out. So we see that the output, the capacitor is lagging in this case. I'm measuring the voltage across the capacitor, not the resistor. So that means that it's not the current in the circuit. And so I'm going lower and lower, and the capacitor is higher and higher. Right, and so it's a little counterintuitive because the resistor now has got a very high Z and the frequency shift is very small. And that's simply because I'm measuring the voltage across the capacitor itself, which is something we do. And we just have to be a little clever to understand the phase shift. Generally speaking, we don't think about it being in front or in back. We don't really care. We just see it. But I want it to be consistent with the notes I'm putting up there. And because we're measuring the we're not measuring the current right now. And the other day I tried setting that up, and I thought this thing flaked out. But in any event, like I said, it's not critical, at least for us in Physics 3120, to be able to tell me who's ahead or who's behind. The only thing you have to remember is that the inductor and the capacitor go in opposite directions. That's it. And you have to interpret, when you're doing a high-pass filter, you're measuring the voltage across the resistor, so you're going to be looking at the current. So here's a note to yourself. When I look at the low-pass, the high-pass filter, I'm going to see the opposite effect here. In this case, the V cap is going from 0 to 90 degrees ahead because this is a low-pass filter. And I'm looking at the voltage across the capacitor. When I look at the high-pass filter, I'm looking at the voltage across the resistor, right? Think of the voltage divider, and it's going to be on the opposite side. So basically, the easiest thing to do is go back and forth with the frequency, notice the behavior, notice the phase shift, and then think to yourself, okay, I expect zero phase shift when the capacitor is not having that much an effect on the circuit. And in a low-pass filter, that means that it's at low frequencies because then the capacitor has a high Z. And it seems weird because you kind of would expect a bigger phase shift. But we're measuring the voltage across the cap, not the current. So it isn't easy, right? I can't put foam rubber on everything. You're just going to have to learn how to interpret what you see. But the most important thing is, what is it that it means when I see the phase shift so much? As a rule, we care more about V out over V in than we do about phase shift. When he said earlier, when we were measuring Z out, that we wanted to make sure that there was no phase shift, we were measuring, we wanted the capacitor not to be part of the circuit, and that's why we need, by making its resistance very little, it was having no effect on the circuit in that instance. In the instance of a low-pass filter, unfortunately, it's the opposite. We want the frequency low. So it's something you have to think about. But you're not going to be held to account with phase shifts. I'm just trying to give you a flavor of where it comes from. Now, notice that the capacitor, in principle, is lags. It's behind, but we just see a case where it didn't. The important point is, though, if we, well, this is not, let's think about this. Right. Eventually, we're going to look at the inductor, but not today. It's a way of also showing you why we do things the way we do. Now, haze gives us a much easier way of understanding it. So now this is not a phasor anymore. All it is the impedance in complex graph. Nothing is going to rotate. So the capacitor is negative, and it in principle is here, but when you add vectors together, you always want them tail to head. And each one of these graphs is a little different depending on whether it's series or parallel and such. But this one is the easiest one to understand. So here's where you see the phase shift and the V out over V in changing, because the V out over V in depends on the length of the resultant. And the circuit itself. And so as in this case, let's see, 2n 3.1, doubling the frequency means that I'm making the capacitors, before it was half and half. You see it was 45 degrees there. Now I've doubled the frequency and halved the Z of the capacitor, and then I double it again. And you see how the capacitor has less and less of an effect. Now, I wonder if I agree with this thing as much as he wants us to. So the top one is the low-pass filter, So at high frequencies, we're going to see that it kills them. And, well, let's go back to the picture. You can see that if I had to think a lot about these phase shifts in my professional career, I'd be able to explain it better, right? Obviously, it's not that big of a deal. But it helps you to figure out where resonances are, especially. You watch the phase shifts. You may hear me talk to you. When I talk to you and help you, I say, oh, look, here's the phase shift. This is where I know something is happening, right? That's the single most important thing you need to remember. As far as the different directions, it's not that important. Okay. I'm going to have to go back over this. He makes a lot of mistakes, and I have to double check what I think about this. Okay, so this is where I said, remember, we need to make Bode plots. So I'm going to stop this recording and start a new one. Let's bring up our spreadsheet.